Good afternoon, everyone. Thanks for coming to this session where I'll be talking about interactive querying with Spark SQL. I assume that most people here already know about Spark SQL, so that is not what we are going to talk about. We are going to talk specifically about how to use Spark SQL to meet interactive querying needs. All right, without further ado, let me get started with the most important thing first, which is about me. I'm Ashish Singh. I'm tech lead on the big data query platform at Pinterest. I'm also an Apache committer, and you may have seen me or my contributions in various Apache projects like Iceberg, Parquet, Hive, Kafka, Sentry. Great. Now that you know about what we're going to talk about in this session and about me, let's get started. Before we talk about interactive and scheduled querying, let's go over what I mean by querying itself. Querying is the process of extracting information from data using SQL. This usually involves computation on data, but that's not really a requirement. For example, we run queries to even understand the data. We usually refer them as metadata queries. In fact, these are some of the most common queries that you will see on any query platform. No one would remember all the table names that you have in your schema, or the columns in those tables, or how the table is partitioned, or if yesterday's partition is available on a given table or not. All such information is retrieved using metadata queries. Now that we understand what we mean by querying, let's dive into scheduled and interactive querying that I have been referring to so far. In very simple terms, scheduled queries are queries that are not executed by humans. These queries are usually executed by a scheduler, something like a cron job or an Airflow DAG. On the contrary, you may have already guessed it, interactive queries are queries that are executed by humans. This is a very simple difference. However, the small difference comes with some pretty large differences in user and system expectations. And so the needs for underlying systems are very different too. Let's try to understand these differences a bit more. Scheduled queries run on a predefined cadence. And so the time a particular query runs, the type of compute it does, data it accesses, resources needed are very predictable. However, with interactive querying, there is no such predictability. No one is waiting on scheduled query results. Sure, there are some SLAs. You want your scheduled queries to finish within a certain time, but there's no human sitting in front of the computer and waiting for a scheduled query to finish, which is usually what users do in interactive querying. Similarly, these scheduled queries are usually tested before they are deployed to production. And so the chances of you running into syntax error or analysis error in your scheduled query is pretty low. Whereas in interactive querying, it's very common. As the scheduled queries run multiple times over a period of time, the ROI of tuning is very high. A badly tuned query will consume more resources, not just once, but like every time it runs. Whereas interactive querying, the tuning is mostly an overhead. If you just want to run your query once, and if you have to run it like 5 times just to tune it, it's a huge overhead. And similarly, for resource efficiency, it is very important in terms of scheduled queries. But for interactive querying, it's the developer's user velocity that is more important. All right. Hopefully, we are on the same page on why scheduled querying and interactive querying are very different. Because of these differences, the underlying system needs to be different as well. This is the part we'll be talking about in the rest of the session. But before we start talking about it, let me make a case on why you should listen to me. In data world, credibility usually comes from the scale at which a problem is solved. So let me give you a glimpse of the scale at which the big data query platform at Pinterest operates. We have over 700 petabytes of data in AWS S3, which is processed by over 150,000 jobs daily. And this is made possible by over 20,000 Hadoop nodes and over 1,000 cluster workers. We have over 300,000 tables in our Hive metastore. I'm not proud of that. We primarily use AWS for provisioning our infrastructure and to store our data. All right, hopefully these numbers got your attention. And let's see. Before that, we have 3 query engines that we support at Pinterest. Spark SQL, Presto, and Flink SQL. Until last year, we also had Hive, but we migrated over 10,000 jobs to Spark SQL and deprecated Hive completely. And if you want to learn more about that deprecation, please come visit room number 211 at 4:45, where my colleague Zaheen will be talking about it. All right, coming back to the interactive querying. So an interactive querying session looks something like this. A user comes in, they have a problem in their mind. They need to first find out, like, oh, what are the data sets and tables that I can use to answer this question? This is what we refer as the data exploration stage. And once the user have found out, oh, these are the tables I need, these are the columns that I'll be joining these tables on, the next step that the user does is like they formulate the query. And once they have formulated the query, they run it with a toy data set, right? They may use sampling, or they may use like a bunch of filters to reduce the scale of the data. And once they have a successful sample query running, they usually run the full query. They get the results, if they're lucky. Otherwise, they have to try a few times, fix the errors, tune the query, and then they get the result. And once they get the result, they analyze the results. If that is what they were looking for, they can exit out of the cycle. But quite often than not, they have to enrich the result that they got with other data set. Or they have to improve the query that they ran in the first place. And so this cycle goes on. Typically, productivity of a user is inversely proportional to the length of these cycles. As such, in interactive querying, we try to keep the cycles as small as possible. So what requirements can we drive from this usage pattern for interactive querying? These are the requirements we drive from the pattern that we saw. We need a seamless query submission from existing tools. For us, these were mostly Querybook and Jupyter. Querybook is an Pinterest open-sourced, a UI-based query client. Then we wanted the metadata queries to be very fast, to keep that data exploration phase cheap. We wanted to fail fast in cases of syntax and analysis errors. We wanted to provide easy access to results, irrespective of the size of the result. We wanted to make it easy for users to handle errors and tune their queries. And when possible, we want to auto-retry queries with appropriate fix applied. OK, before we start discussing how to fulfill these requirements for interactive querying, let's take a look at the architecture diagram of scheduled querying with Spark SQL at Pinterest. It will also be interesting to learn how it stands against our interactive querying requirements. All right. Pretty obvious from this diagram, we use Apache Yarn as resource manager at Pinterest. But let me walk you through a scheduled query execution lifecycle at Pinterest. A scheduled query is submitted through a scheduler like Airflow by making a call to job submission service. Job submission service is a custom service that we wrote, which essentially is an interface to the Yarn cluster. Once a query comes to job submission service, what it does is like it wraps the query execution in a distributed shell application. And then it asks the resource manager for a container to run the distributed shell application. Yarn allocates a container and returns its information to job submission service. We also refer job submission service as JSS. So JSS then runs the shell application in this allocated container, which in turn runs a Spark CLI command. The Spark CLI requests a new container for resource manager that runs the Spark driver in that container. The driver performs query planning, for which it talks to HiveMetaStir and keeps updating job submission service of the query progress on each poll. Driver requests more containers for executors as needed for execution. In the step 8, executors perform required tasks as requested by the driver. And at the end, driver returns the results to the job submission service, which returns the results to the client. Or if there's an error, then they return the error message. Let's see how does this architecture does against our interactive querying requirements. So this was our requirements for the interactive querying. And by the looks of it, it doesn't look good. But let me talk a little bit more in detail about why it's not great. So in this architecture diagram, if you see, like we are talking about 2 container allocations. So when the job submission service needs to run a distributed shell application, it has to wait for a container to be allocated before it can execute or start running the distributed shell application. So that's the first allocation. When the Spark CLI starts up, it needs another container for it to be able to run the Spark SQL driver. That's the second container allocation. Because of this, even if you were to run a couple of seconds of metadata query, you may end up waiting for tens of minutes for container allocations if your yarn cluster is busy. And similarly, if you had a typo in your query, it will take you tens of minutes before you would know, oh, there was a typo in the query. Just kills the developer velocity. Similarly, like though we don't have any client, the JSS, we only had a Java client, which doesn't really integrate well with the existing tooling like Jupyter and Querybook. It did not provide an easy access to the results. It did provide access to the std out of the driver, from which the client can choose to pass out the results. Not very scalable, not very flexible. It did provide some basic error handling and tuning sessions based on Dr. Elephant, but it was very basic. And the auto error handling and retries is basically limited to the scheduler retry mechanisms. So overall, I think this architecture did not fare well for our interactive querying needs. As such, let's look at the other architectural choices we looked at. We looked at 4 choices. The first one is what we already talked about. Second is using Spark's thrift server, which is similar to Hive Server 2 from Hive World. It does provide a good connectivity with the JDBC, ODBC-based clients. However, the reason we did not choose this architecture or approach is because it did not provide good enough isolation between the queries. We used to use Hive Server 2 at Pinterest before, and there were instances where one query running on the Hive Server 2 would really kill the instance. It will cause a kernel panic, and then the instance will go away, and then that essentially kills all the queries that were running on that instance. So we did not want to repeat that mistake. In the option 3rd and 4th, we looked at Apache Livy. Apache Livy essentially provides a REST interface to your Spark cluster. And the only difference between 3rd and 4th is the 3rd uses the batch sessions of Livy, and the 4th uses the interactive sessions. The interactive sessions of Livy provides us a lot more flexibility when it comes to how we can use the session. It provides us capability to start the session. It essentially starts a REPL, and then like whenever we have to run something, we can send it to Livy. And when we are done with it, we can close it. We decided with the 4th option because of its flexibility, which will come handy in enhancements we built that I'll discuss shortly. All right, let's take a look at the architecture diagram of interactive querying with the 4th choice. OK, let me walk you through the interactive query execution lifecycle with this architecture. Query clients submit the interactive Spark SQL query, which then gets routed to Apache Livy. Livy asks for a container for a resource manager to run the Spark SQL driver. And in this container, what actually is running is a remote Spark context, which starts the Spark SQL driver. And after that point, Livy just talks directly to the remote Spark context. And beyond that, the execution of Spark SQL remains same as the previous discussion we had. So even with this architecture, we are still spawning a yarn container before we can start our query execution. Let's look at like how does this architecture fare against our scorecard. Wait, this looks worse. It looks worse than what we were getting from our existing architecture of scheduled querying. That is true. However, we chose this architecture not due to what we get out of the box, but because of the low cost and effort to get what we wanted by using what we get out of the box. We'll be talking about some of the enhancements we added that really enabled us to meet all these requirements. The first one is the seamless query submission requirement that we had. Livy provides a RESTful API. And what we did is like we added a DB API to compliant client using those RESTful APIs. As we were moving from Hive to Spark SQL, our clients, or query clients, were already using PyHive. With this client, we were able to drop in and replace PyHive with our BigPy client, and seamlessly users were able to start querying with Spark SQL instead of Hive. The second problem is the fast metadata queries. As discussed, waiting for container allocations can significantly add latencies up to tens of minutes in query executions. Additionally, starting a Spark context can take time too, because it had to download all the jars, it has to create a connection with Metadata, load all the functions, etc. And it gets really worse when you have like 300,000 tables. So I think like we have like tens of thousands of schemas, and each schema can have their custom functions in it. To alleviate these concerns, we implemented a local session pool in Apache Livy, which maintains a pool of Spark sessions running in local mode, which essentially takes advantage of the fact that for your metadata queries, you don't need executors. All you need is a driver. Whenever a user submits queries that are only metadata queries, we utilize one of these local Spark sessions to run their queries. This helps us avoid the cost of yarn container allocations and Spark session startup cost as well. For this to work, we enabled Livy to distinguish between DDL queries and DML queries, and also had to add capabilities like automatic GC or stale sessions and launching new ones whenever we expired one. We had to add health monitoring on these sessions. We had to asynchronously load the Spark context to avoid cost of establishing HMS connections while executing users' metadata query. The end result was that we were able to reduce metadata queries latency significantly to a point where it wasn't a concern anymore. Moving on, our next requirement was fail fast. For each user DML query that are non-metadata query, what we did is we started taking advantage of that local Spark session pools. Whenever a query comes to Livy, we check like if it is not a metadata query, we would start 2 executions of it. The first execution would be the real execution that runs on the Spark yarn cluster. But in parallel, we would start and explain on that query in our local Spark sessions. With that, very quickly, we'll see if there is any syntax error or there's an analysis error. And we would catch that and cancel the remote execution of the query and return the error to the users. This helped us reduce the time that users would have to wait to even see the typos in their queries significantly. The next requirement we had was easy access to results. Livy only returns maximum up to 1,000 rows by default. We made this configurable that users can now set in their queries. However, there's a good reason why Livy added this limit in the first place. It is to allow Livy not choke on memory by someone running a select star query on a very large data set. So how do we handle large results then? We started wrapping all these select queries with an insert into directory statement. And by doing so, this directory for us was on S3. By doing so, we made it easy for all executors to write the results directly to S3. And this alleviates not the concern of memory on Livy, but also on driver. Because now the results, that huge result set is not flowing through driver or Livy at all. Because like we had our custom client, BigPy, we made changes to it so that like it can directly pull the results from the S3 location. So this helped us meet our requirement for the easy access to results. But not just that. It also enabled us to add features like, say, a user ran a query, they generated a large result set, and they want to do further analysis. With just a click of a button, we allow them to create a table on top of the result set so that they can continue their analysis. Because the data is already on S3, we know the format of the data, so creating a table on top of it was very easy for us. Fixing Spark query failures can often become a daunting task of skimming through the driver logs, executor logs, yarn container logs, GC logs, looking at metrics, etc. Some of these common failures can be identified by looking at various logs and metrics. We utilize yarn diagnostics and Spark error messages to identify common memory-related issues and provide a recommendation on how to handle them. An issue with Livy interactive sessions in cluster mode is that they consistently report a success status back on the Yarn application master. To mitigate this issue, we track the status of the final query statement that ran and failed, and we fail the entire Yarn application with that error message. So that Yarn diagnostic message correctly captures the failure of an application. We added error classifiers for the errors we know how to handle and can easily identify based on error message to Dr. Elephant. And then we enabled our clients that whenever the query fails, they would poll the Dr. Elephant to get the recommendation on like, oh, what was the error? Like, well, how should I handle it? These like very naive error handling recommendations like increase your executor memory, increase your driver memory, increase your broadcast timeout, or just turn off your broadcast. These are very small fixes, but only for people who knows about Spark. Not everyone knows about Spark. At least like a lot of our users don't. And we don't really expect them to be aware of the Spark internals. I mentioned some time back that human time is way more expensive than machine time. And for this very reason, our interactive users tend to run their queries with very generous resource configs. Though it is true that having more resources, like memory, would likely reduce the chances of an OM, however, sometimes it leads to Yarn container location delay, leading to wasting more time for the users, even when they don't realize it. To elevate this concern, we added visibility into resources like memory during query execution and flag users to take action when we detected memory being underutilized by a large fraction. Or if it is running very close to the container limit, at that point, we also ask them that, like, yeah, you are running very hard on the memory. This makes users to be conscious of their resource demands, increase speed of querying by reducing container allocation times, and reduce resource wastage. We didn't stop there. We thought about that. OK, so we provide these recommendations. We have ways to figure out like what recommendations to provide. And we expect that users will handle that. And then for the next requirement, we are planning to automate this. This is a work in progress. We haven't done this so far. For auto error handling and retries, we are planning to add error handler in Livy itself. This handler would look at known error types and would decide to rerun a query. We already have the error handlers, right? Like based on that, we generate the recommendations. The next step for us is obviously automatically apply the fixes and then rerun the query. Sure, not all queries can be retried. Not all the queries are idempotent. And for that very reason, this will be an opt-in feature where users can opt in and say that, yeah, I want to retry my queries during failures. For example, if executors need more memory, we rerun the query with more executor memory. Or if a query timed out while broadcasting, we increase the broadcast timeout up to a certain limit. And after that, we just turn off the broadcast. OK, so after all these improvements, let's get back to our requirements and see how we are doing. OK, so we were able to meet all the requirements with the architecture that we chose. This is what we wanted to see in our interactive querying. Our interactive querying solution not only met all the requirements we had, but also enabled us to quickly add more features to improve dev velocity. For example, one of the requests was, can we bridge the gap between the ease of SQL and the flexibility of code? We said yes. And we added support for users to write Scala UDFs along with their queries. This was a very easy addition that we were able to do because of our design choice. Livy, as we said, like Livy with interactive session gives you access to the REPL. So we keep the session open, and we utilize the REPL to register the user's UDFs, and then we run the query. We're excited about the things we will build to make querying even more successful in future. Just to recap, this is what our interactive querying platform looks like. And this is the entire Spark SQL querying platform's architecture diagram. With this architecture, we are able to scale our querying needs as needed. More importantly, we are able to adapt our systems to meet evolving user demands. With that, I'm done with my slides for this session. Hope all you were able to enjoy and learn from our experience on building an interactive querying platform with Spark SQL. I'll be happy to answer any questions.
All right, thank you very much. Do not have any questions so far? Right.
Thank you. Excellent talk. So at the keynote yesterday, I believe they announced the SQL API. Did you see that keynote?
I haven't. You said it's SQL API.
Yes.
Okay.
Okay. So if you didn't, I'm just curious to hear how that announcement would relate to what you guys have been up to here.
We'll look that up.
Okay. Perfect.
Is it like a very Databricks centric thing, or it's
I don't know.
okay?
We can look it up. Thank you.
Thank you.